Welcome back everyone. In the last lecture, we had seen how to find out the controller gain K given a system and some performance criteria. We also found few examples in which we were not able to find out the controller gain K that resulted in the desired performance for that system. Today, we will take up those problems, the problems that we could not solve, and we will see how can we design controllers for those cases. In the process, you will learn the controller design procedure using root locus. Let us dive into the quadrotor problem that we had. The problem statement was we have a quadrotor which can fly only in the z direction, and we want to design a controller K or find out a value of K, controller gain K, such that 40% overshoot is allowed. So, basically the question here is, if you give some desired altitude, say suppose you give 1 meter as your desired altitude, we want that the output should reach 1 meter, and while reaching that it can overshoot 1 meter by 40%, but not more than that. So, let us try to solve this problem. If you remember, in the last lecture we have seen that this problem is not solvable with a simple gain block K. The reason was, if you find out the desired pole location, which comes out something like this, you can find that the desired pole location will be on the complex part, on the left half of the complex part in the complex plane, and the closed loop pole location, when you look from the root locus, can be seen to be only lying on the imaginary axis. So, which means for any value of K from 0 to infinity, you will not be able to place the closed loop poles of the system at the desired pole location, the desired pole location being this. We have seen this in the last lecture. So, how do we solve this problem? So, the idea is that since K was only a simple gain was not able to make the root locus pass through this point, why do not we go ahead and change the shape of the root locus or the branch's direction such that the direction passes through this point. Now, how can we do that? You see, if we change the gain K here by something, say for example K by S plus A, that means I introduce a pole, additional pole into the system, then maybe we will be able to solve the problem. Or maybe if I add a 0 into the system, maybe I will be able to solve the problem. Now, while doing so, what are we trying, what we are doing exactly? If you suppose you introduce a pole into the system, so basically K is getting replaced by K by S plus A now. So, what is the open loop transfer function? If you leave out K, then the open loop transfer function will come out to be 1 by S square S plus A. And for this transfer function, if you draw the root locus, you can have some root locus. If that root locus passes through this point, maybe you will be able to then solve this problem. You see, if you introduce a pole, suppose the pole is at minus A, then how will the root locus look? Let us think about that. Okay, we do not need an exact sketch, just a approximate sketch is good enough. You see, this is the desired location, these are our open loop poles now, because this is the open loop transfer function GS HS in this case. Of course, G I have, this is the new G means I have taken this S plus A with 1 by S square. So, I am changing this block into K 1 by S square S plus A. This is what I am doing. Now, how does it help us? Notice, now that we have 3 open loop poles, we will have 3 root locus branches. So, 3 RL branches. Okay, the first thing is to notice that. The second thing to note is, since we have 3 RL branches and we have no finite zeros, these branches should go to infinity. So, we will have 3 asymptotes in this case. Now, what are the angle of asymptotes? That would be given by plus minus 2k plus 1 into 180 degree divided by total number of open loop poles minus total number of open loop zeros, which is equal to, in this case, plus minus 60 degree and then 180 degree. These are the 3 angles that you will get. You can go ahead and check, these are the angles you will get. And what will be the centroid? Centroid will be real part of the open loop poles, summation of the real part of the open loop poles. So, minus a plus 0, summation of the real part of the open loop poles minus summation of the real part of the open loop zeros, there are no zeros in this case, divided by number of open loop poles minus number of zeros. So, this is the centroid and the centroid comes out to be minus a by 3. So, maybe somewhere around here, say. Okay. So, that means at this point you will draw the asymptotes in this form. So, what will be the root locus like? The root locus will be something like this. Okay. And you see, no way that this root locus will pass through the desired pole location. One more important thing to note here is that here in this case, both these branches always lie to the right half of the complex plane. That means, for any value of k, you will always get some closed loop poles on the right half of the complex plane, which we know already that will be an unstable system, because the closed loop poles must lie on the left half of the complex plane for the system to be stable. Okay. Although stability was not given as a performance criteria in the problem statement, but certain things are always there. So, one of the point is stability. You should always ensure that the closed loop system is stable, and number 2, in most of the cases is that the steady state error must be 0. That means, at the end, if you give here 1 meter, then y must reach 1 meter. It should always get to the desired location. So, these 2 parameters are in general always there. Stability is always there, it has to be there, otherwise you will not be able to use that system practically. But steady state error, in most of the cases, we always assume that steady state error should come out to be 0. Okay. Now, we can actually go ahead and do this simulation. So, suppose these are our desired pole locations. Okay. I mean, I have taken just any arbitrary desired pole location, and here there are 2 poles. And this is the third pole that has been introduced. This is minus a. Okay. This has been introduced by the controller, and you see, in this case the value of a is 0.31, which means this is at minus 0.31, and you can see there from the root locus itself that the root locus branches are on the right half of the complex plane. If you change the position of the pole, you see I am changing the position of the open loop pole introduced by the controller, the value of a, you can see that whatever be the value of a, these 2 branches always goes off to the right half plane, and there is no way that they are going to cut this desired pole location. So, using a pole, we are not able to solve this problem. Fine, no problem. Let us go for a 0 then. Okay. Let us introduce a 0. Now, will a 0 solve this problem? Again, since you have now you have see 2 open loop poles. So, that means, so again, what will be the new open loop transfer function? The new open loop transfer function will be s plus a by s square. So, you have to draw the root locus of s plus a by s square. If the root locus passes through the desired pole location, we can find out the correct value of k. Okay. Again, do not get confused as to, I mean, I am adding new things here. At the end of the day, I have to draw the root locus of the open loop transfer function. What I am doing here basically is, instead of k, I am replacing it with some other transfer function. Instead of a constant gain, I am changing it to some other transfer function. And why am I doing that? Because if I change k to say k into s plus a, then there will be a new root locus, because the root locus branches will change directions now. Remember, with just k, the root locus branches were not even passing through the desired pole location. So, somehow I have to change the direction of the branches. Okay. Now in the previous case where I introduced a pole, what was happening? You could see that when I am changing the value of A, I am taking the pole away from the origin, still the branches were going to the right side. Okay, let us see what was the influence of the pole. Suppose there was no pole. Okay, suppose it was the controller was K and the plant transfer function is 1 by s square. How was the root locus? The root locus was passing through the imaginary axis. As soon as you introduce a pole, you could see that the root locus, instead of the imaginary axis, it went to the right half. That means it is almost like when you are introducing a pole, it is repelling the branches towards the right side. Now let us come to the 0 case. When you are putting a 0, so what does it mean? So you are replacing k by k into s plus a now. Okay, so the new open loop transfer function becomes s plus a by s square. This is the new open loop transfer function. Now in this new open loop transfer function, let us see how many branches will be there. So how many root locus branches will be there? S plus a by s square is your open loop transfer function. So we will have 2 branches, right? We will have 2 root locus branches because there are 2 open loop poles. Now one of these branches will be one branch will terminate at minus a, right? Why? Because there is a 0 here, so one of the branches must terminate at that point. Okay, and the second branch, one branch will go to infinity. Now plus infinity, minus infinity, we don't know. So let us see. How do I know that? We have to look at the angle of asymptote. So what is the angle of asymptote in this case? Plus minus 2k plus 1, number of open loop poles by number of open loop zeros into 180 degrees. So it will come out to be 180 degree, right? Similarly, what is the centroid in this case? The centroid will be the real part of the open loop poles minus the real part of the open loop zeros divided by number of open loop poles by number of open loop zeros. So this comes out to be a by 2. So somewhere around, say here. Okay, and how is the asymptote line? The asymptote line is something like this. So how is the root locus looking now? At this point the root locus won't lie, right? Because at any point you here take here, to the right of this there are even number of open loop poles and zeros. So the root locus won't lie from minus a to 0. So that means the root locus must go something like this. Again, this is not an exact drawing. You can find out the breakaway points, all the procedures that we have already seen. You use that and you will see that the root locus will look something like this, right? Now you see from here, one thing that you can notice is that at some point maybe the root locus might pass through this point. There is a chance. Okay. Now what is the effect of introducing a 0 into the root locus? As soon as you introduced a 0, you see in the previous case when we had 1 by s square, the root locus branches were on the imaginary axis. Now when you introduced a 0, the branches are getting pulled towards it, because we know that one of the branches will terminate at that 0, right? Whereas when you introduced a pole, it was repelling the root locus, right? So depending on what you need, you have to decide how to solve this problem. So let us see, when we change the position of A, how does the root locus change? Here again there are the two open loop poles of the plant, and then you have the 0 that we have introduced. At present 0 is at 1.24. So if we change the position of the 0, you will see, if I change the position of the 0, I am changing the position of the 0 here. You can see this, the position of the 0 keeps on changing, and you see at some point the root locus does pass through these points. Remember, these points I have just taken arbitrarily now. We will take exactly what desired position we have, but we know that the desired position will lie somewhere around in the second and the third quadrant. So I have just chosen arbitrarily as this, just to show you that okay, by changing the position of this 0, I would be able to pass the root locus through that desired pole location. Now suppose I pass the root locus to the desired pole location. Now what? Now after that what? Suppose I have already done that. So suppose I found out, I came up with a value of A. Okay, so s plus 3.62 by s square. Now once I have that, now I have to just find out the value of k, which I can do, right? Magnitude criteria at this point, at the desired pole location must be equal to 1, and that will give me the value of k. Basic idea is that you influence the root locus some way so that it passes through the desired pole location, and once it passes through the desired pole location, you just have to find out the value of k. That is the basic idea of designing controllers using root locus. Now we know that introducing a 0 will solve the altitude control problem. Why is it an altitude control problem? Because I want a controller that fixes the altitude of the quadrotor. Okay, so let us try to solve this problem by introducing a 0, because a pole was not able to solve the problem. So the first thing is that this was the desired pole location, right? This was the desired pole location that we took. Now of course in the desired pole location there is a variable omega n, so we need to fix it first, right? Because we should first know exactly which desired pole location I need. And remember, omega n here can be anything now, any positive number, right? Remember what was omega n? Omega n is given by some semicircle, right? So on this semicircle, so each semicircle corresponds to a particular value of omega n. So you can choose any of these semicircles. So I will choose, say for example, I choose omega n equal to 10. I mean that is just randomly I have chosen omega n equal to 10. So as soon as omega n is 10, my desired pole location becomes minus 2.8 plus j 9.60. This is my desired pole location. Now if this is my desired pole location, for the root locus to pass through this desired pole location, it must satisfy the angle criteria. Let me call it SD. So how do I check whether it satisfies angle criteria? Again remember, my open loop transfer function is this now. Okay, if the root locus of this s plus a by s square has to pass through this location, the angle of this function at SD must be equal to some odd multiple of 180 degree. Similarly, the magnitude of this at s equal to SD with k must be equal to 1. Let us find what is the angle subtended by the open loop zeros and the open loop pole in this case, and from you can directly see that this would be tan inverse of 9.6 divided by a minus 2.8. So tan inverse of that, and here there are two poles here, so that will be negative minus 2 times of pi minus this angle. So this angle will be tan inverse of 9.6 by 2.8 equal to minus pi. I have taken minus pi, you can take any other odd multiple also, it is up to you what you take, but finally the answer will come out to be the same, and in this case the answer comes out to be 17.8571. Great. So we have a value of a at which this the root locus will pass through this point. So again, now that I know that this will be my this is my open loop transfer function. So now k multiplied by this and evaluated at SD must give me 1. So by using magnitude criteria, I can find out the value of k. I will show you how to do it in MATLAB. You can do it directly by hand calculations also. First we will write down the transfer function. So here is the, you know how to write down the transfer function by now. So this is the transfer function. Now at this point, so this is how we can write complex numbers. So I am writing down the complex number, this complex number, this is the real part and the imaginary part. Once we have written down the complex number, so then we will evaluate it. Now evaluation is done by eval fr. Okay, see, remember this part I have defined as GS. This part you can see that this part I have defined as GS, as you can see this eval fr, this transfer function at the point SD will give you the complex number. This is the complex number that you get. So now this has been evaluated. So k into minus 0.1786 magnitude is equal to 1. So what we will do is we will find out this can be written as k absolute value of this, we will find out the absolute value of that. You see I am finding out the absolute value. So absolute value of this number. So and then 1 divided by that will give me the value of k. So the value of k comes out to be 5.6. You can do this entire thing using hand calculations also. I am just showing you the procedure to do it in MATLAB. So k equal to 5.6 is your answer. So what is the final transfer function that you get? So the final transfer function is 5.6 s plus 17.8571 into and this is the plant that you had. This is the actual quadrotor that you had, and this is the transfer function of the controller that you came up with. Do we reach 40%? Let us use the same procedure that we did earlier. I have already defined G and C for you. So then we just have to go ahead and write down the closed loop transfer function. So, the closed loop transfer function will be given by the feedback function that MATLAB has, we can use that. So, feedback C into G comma 1, and this gives me the closed loop transfer function. And finally, the pole 0. What are the closed loop poles and zeros? The closed loop poles and zeros you can see will come up to be these. Now, you see this is exactly the point where we wanted the closed loop poles to be. However, you can also see that there is a 0. This 0 has showed up as the closed loop 0. By the way, why does this 0 shows up as closed loop 0? This was an open loop 0, right? But you can see what is happening. So, what is the closed loop transfer functions? This, if this is GS, CS GS divided by 1 plus CS GS, right? Now, if what is CS? Suppose CS is N1 by D1, numerator by denominator. So, this becomes numerator 1 by denominator 1 multiply G is also say N2 by D2 divided by 1 plus N1 D1 multiply N2 D2. Now, if you multiply both sides, you are left with N1 N2 divided by D1 D2 plus N1 N2. Notice this is the closed loop transfer function, and you can see in the closed loop transfer function the numerator is the product of the numerator of this transfer function and this transfer function. So, the zeros will be just roots of N1 and N2. So, which means the roots of this multiplied by 1 and the roots of this is what? Minus 17.8571. That is why the open loop 0 itself comes out to be the closed loop 0. Why is that important? That is important because if you choose your open loop 0 further away from the closed loop 0, at least 5 times away from the closed loop zeros, then you know that second order approximations will be valid. So, you should always try to choose it further away from the closed loop zeros. To closed loop zeros as in the desired pole locations. So, now, if you see the step response of the system, the step response you will be able to see what will be the exact peak percentage. Again, remember, because of this 0 there might be some effect on the step response of the system. So, the step response here, let us see what the step response is. So, right click and then characteristics peak response, and when we click on the peak response you see that it is 47.1. Okay. So, we have achieved 47.1% overshoot. Okay. The target was 40%. We have not exactly got to where we wanted to, and so we will have to fine tune now. We will fine tune this controller so that we reach to 40%, and for that we will use something called the CSD app in MATLAB. Okay. Control System Designer app we will use in MATLAB to get to that 40% mark. So, let us go ahead and do that. So, you can see that I have already defined the transfer functions here. G is the open loop transfer function of the quadrotor or the plant transfer function. C is the controller that we came up with. If you go ahead and see, this is the controller that we came up with. So, let us go ahead to apps, click here and then go to control system designer. So, control system designer toolbox, this is a toolbox used to design controllers for CISO systems, single input single output systems. So, let us just click on this. So, when you install MATLAB, ensure that the CSD toolbox is there. Okay. So, this is how the toolbox looks like. I do not intend to use Bode plots now. So, I will just cut down this, I do not need that. Now, in the toolbox section you can see lot of things. On the left hand side you can see different blocks here. There are responses, root locus editor we have and step response you have. What is the step response? Step response is from R to Y. So, the first step here is go to edit architecture, click on it, and then here you can see different architectures of controller and plant. So, closed loop architecture. So, this is one of the architectures, there can be other architectures also. Now, in this case the first architecture that is there is the default one, the one that we generally use. Okay, there can be others also, but for this course we are just limiting ourselves to this architecture. Now, in this architecture you can see This C block is your controller block, G is your plant, H is the feedback transfer function, F in some cases F is required, but in our case F is 1. So, by default F, C, G and H are all 1, okay, and you can see the step response was from R to Y, right? It is written R to Y. See, R is the reference signal here, Y is the output. So, that is the step response that we want. If you want, you can also find out what is the output from U to Y. So, in that case, you will have to keep on changing the responses. So, it's like DU to Y. You can see on the left there are responses, but that is not what we are looking into today. We want to look for the step response from R to Y. That means R is replaced by a step input and we will see what the output is. Now, you see, I have to change the value of C and G, right, because G is 1 by S square and C is the one that we have just come up with. H will be identity, F will be identity. So, I will not choose those because those are fixed already. So, C, let me click on this. Once you click on this, you will see that the transfer functions that we have defined C, G and S are already there. So, I just have to take the C transfer function. Remember, you should define the transfer functions on the window, on the command window first, so that you can use it directly, okay. So, let me just click on C and then do import. So, you are able to import it, then go to G and then click on G and then again place import, and then finally now see everything is in place. So, I will just press OK and you will see that the root locus has changed, and this is the step response. You can see there is a pink line, pink dot here. This is the value of K, okay. Remember, we had K 5.6, right. This is the value of K at which this is the response. If you change this on this root locus, you remember, right, what is this root locus? Root locus is nothing but at different points the value of K is different, and corresponding to that whatever closed loop poles are there, that point represents those closed loop pole locations. So, here this is 5.6 was this. You can go to that and click on that. You can see on the bottom screen, at the bottom of the screen, you see there is a drag this closed loop pole on along the locus to adjust the loop gain. So, now the current location is minus 2.8 plus 9.6 I. That is exactly the location we designed it for, right. And the damping is 0.28 now, and the natural frequency is 10. The natural frequency is 10 because we have chosen it to be 10, okay. So, I am not changing it right now, just let me just release that point. So, when you place on that, you will be able to see that. So, left click on that, okay. If you release it, then it is released now. Now, you see what we can do is we can go to the step response and on right click on it, okay, right click on it and go to design requirements. In the design requirements, you click new, okay, because we will put the desired requirements that we have now. So, what is the design requirement that we have? We want that our overshoot should be 40%, right. That is the design requirement we have, okay. And you can see design requirement type, there are different design requirement types also. We want only the step response design requirements, we are not dealing with anything else. So, the design requirement is this, overshoot 40%, settling time and rise time we did not have any requirement on that. So, we will not write it for now. So, this is 40%. Once we give that and you press OK on it, you will see that this is the overshoot line. So, the step response should not go above this line, but we know that we have already seen that we were getting 47.1%, right. So, hence the step response was going above this line, which is what we saw. We have to somehow change the controller such that the step response comes within this line, okay. So, let us try to do that. How can we do that? You can go to the, see, there are two things that we can do. There are two parameters that are in our hands. One is the value of the 0 location A and the other is the K location. Since we have fixed A using angle criteria already, let me not touch A. You can always use A also, but let me keep A as it is and let me see with just gain adjustment. That means only by changing the value of K will I be able to achieve this this objective of 40%. So, I will have to click on that again, click on that pink colored box that you are seeing, that is our K. I clicked on it, left clicked on it, and then I change its position, and you can see as I move it away from the imaginary axis, you see the step response is coming within bounds. You can see the change in the step response, and now we are exactly at 40%. I will release my hold here, and you can see we are exactly at 40, exactly or somewhere near 40%. You can zoom in, you can go to the step response, you can click on zoom here, zoom in, and then you can zoom in here by left clicking. You will be able to see the zoomed output. You see, oh, it is not exactly at 40%. We have some leeway again. We can actually go a bit more, and now I am at 40% exactly. Okay. So, this is how we can go ahead and design the controller. Now, what is, so I have changed the value of k, right? Now, I have a new controller. So, let me see what the value of controller is. How do I see that? Go to the left panel and see we have changed, right? Remember, G, H and F we have not touched. We cannot touch that, right? Those are plant parameters, right? Plant and feedback. So, now we will just go to C and click on it, and you can see at the bottom the value has changed to 9.052 S plus 17.886, or it is exactly 8571 actually. So, this is the controller that we have designed. So, you see I just changed the value of k and I was able to reach 40%. So, now I can export this C by going to export, then export tune blocks. If I export tune blocks, you see I just want to export the C value here. You click on this, you can give a name, different name. So, export as say C tuned. Okay, let me just name it as C tuned. So, I am exporting C with a new variable name C tuned. You can keep the same variable name also, then there will be a message box that will pop up which will say that you already have a variable with the same in the workspace. So, would you like to overwrite it? But in this case I do not want to do that. So, I just write it down as C tuned. So, once I click on export, this has been exported to the workspace, and you can now see if I write C tuned, this is the transfer function that you get, and C is the one that we had designed. Okay. So, C is the transfer function that we came up with, this is the transfer function that we came up with, and this is the one that has been tuned. Okay. So, let us see what is the difference in the step response now. So, for that I will first define closed loop transfer function C into G1. This is the old closed loop system, and let me define the tuned closed loop system, tuned as C tuned. Now I am replacing C by the tuned controller. So, let me call that. Then let me see the step response of closed loop, the original as in the one that we designed initially. This was the response. Okay, and now let me on top of it, so I will use hold on to the plot, and then on top of it let me just place closed loop tuned. So, let us see how the output looks like, and this is what it looks like. You can right click and go to characteristics and peek. So, you can see that now this 47.1 was my original response, and 39.9 is the one that I have found out after tuning. So, this controller will help me go to the exact point, but with maximum 40% overshoot, not more than that. Okay. Finally, we were able to solve this using 9.052 as the gain here. So, this becomes your final controller that you have designed, and you have achieved exactly 40% overshoot, right. So, this solves the problem that we started off with. Okay. And you can see that the idea was initially analytically you find out the controller that you want to design, and then you fine tuning it to get to the correct controller, the exact controller that you want to get to using the toolbox that we have used. If you do not have the toolbox, no problem, then you just, once you have found that okay, I am at 47.1% overshoot, you keep on changing the value of k so that you can reach to that particular value. That is how you can design the controller. So, we will end today's lecture here itself, and we will take up the other problem that we could not solve. The problem was we had 1 by s plus 2 into s plus 4 as the transfer function, and we had to achieve two specifications, 40% overshoot and 2 second settling time. We were not able to solve that problem, if you remember. Go back to that lecture and check why we were not able to solve that problem. We will take that problem up in the next lecture. Thank you.